All right, in part C, we're going to look at how well does the line fit the data using S and R squared. If we use a least square regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals is given by this lovely equation. This value gives us the approximate size of a typical prediction error. So from the can tapping example, the standard deviation of the residuals was s equals 5. So we interpret this value. We'd say our predictions will typically be off by 5 milliliters of soda when we use the regression line relating the amount of soda remaining and the tapping time. So structurally, your predictions will typically be off by whatever. In context here, when using the regression line relating, and then you make sure you define the two variables. So we have the set of data we've collected where we have used Ford F-150s. We have the miles that they were driven and the price. Okay, and there's my least square regression line. Suppose we randomly select a used Ford F-150 that was on sale. What should we predict for its price? The figure shows the scatter plot. Another horizontal line right here is the average price of all of these. This is the average price. But if we don't know the number of miles for this new truck, pretend we don't know, how can we predict the price? All right? We know the average price, the Y bar, is $27,834. That's the average price of these trucks. And that's what the green line represents. But if we don't know the mileage on the car, how are we going to predict the price? What should we do? Our best strategy is to use the mean price of the other 16 as our prediction. Now, so what I've done is make this line right here the mean Y value and look at all the points in relation to it, kind of like a residual plot, but I'm not using the regression line. I'm using the average of the Y values. So you can see I have my squares of these residuals. Okay? Now, if I add up the squares of these residuals, this is this equation right here. It's the sum of each observation minus the mean squared. And it's this giant number. This quantity measures the total variation in the Y values from their mean. Okay? This is also the same quantity that we use when we calculate the standard deviation of the prices. Okay? Now, that's total variation related to the mean. But that's not the full idea, so let's keep going. Now, if we learn the number of miles driven on the additional truck, then we could use the least square regression line to predict the price, right? Well, how much better does the prediction line do at predicting the prices than simply using the average of the Y values of all the trucks? This graph reminds us that the sum of squared residuals for the least square regression line is this right here. Right? There's our squared residuals, and we add up those areas. In this case, this is the area we get. This is the same quantity that we use to calculate the standard deviation of the residuals. Now, the ratio of these two quantities that we've talked about tells us what proportion of the total variation in Y remains after using the regression line to predict the values of the response variable. Now, that's a mouthful. I know that. So we know that is the sum of the squares when they're compared to their mean, and here's the sum of the squares compared to the regression line. So in this case, what we're going to do is look at the ratio. Here's the sum of the squares based on the regression line versus, on the bottom, the sum of the squares based on the mean of the Y values. So you'll notice there's a difference in the variation. There's a lot more variation with the means versus the regression line. So what's the ratio? How well does the regression line work? Well, there's still, when I divide these out, I find out there's still 0.336% of the variation out there. Okay? That's not accounted for. All right, this means that 33.6% of the variation in price is unaccounted for by the least square regression line, where x is the miles driven. This unaccounted for variation is likely due to other things like age of the truck or its condition, or there's all kinds of other factors in pricing a truck, right? So taking this one step further, the proportion of total variation in Y that is accounted for by the regression line is this. 1 minus what is not accounted for gives us 0.664. Now, we interpret this by saying this. We say 66.4% of the variation in price is accounted for by the linear model relating price to miles driven. So the coefficient of determination, we abbreviate as r squared. It's the fraction of the variation in the values of y that is accounted for by the least square regression line of y on x. Again, you don't have to know the formula. You just got to recognize this is what it is, and this is how we interpret it. So you're going to take the r squared value they give you, make sure you put it in a percentage form, and you say, whatever, r squared percent of the variation in the price of the truck is accounted for by the linear model relating price of the truck to the mileage on the truck. Whatever it is in context, make sure you include the appropriate context. So how is r squared related to r? Let's first address this question. So r is the square root of r squared. So to know if it's positive or negative, you got to look at the scatter plot, or you could also look at the slope. If you have the equation of the line, if the slope is negative, then your r is negative. If your slope is positive, r value would be positive. But it is just the square root of r squared. Now, r squared and s both measure how well the regression line models the data. It's just two different measurements. S is measured in the units of the response variable, while r squared doesn't have any units. And neither one of them address the form or the shape. Okay, they don't tell us if it's linear or not. That doesn't. So going back to our McDonald's example with the beef sandwiches, we were comparing grams of carbs to grams of fat. So S was 6.98 and R squared was 0.553. Calculated for us, we just have to interpret them in context. So let's do S. Our predictions will typically be off by about 6.98 grams of fat when using the regression line to predict the amount of fat in beef sandwiches using carbs. Okay, typically be off is a key phrase there. Now to interpret r squared, we would convert it to a percentage. We'd say about 55.3% of the variation in fat grams is accounted for by the regression line relating fat grams and carbs in McDonald's beef sandwiches. So the variation in your response variables, which you're addressing here.